cool things off. Thank you, Nathan. Why are there always more cooling fins near the exhaust port of a cylinder head? Right. So if you're looking at the spot with a lot of fins, you're looking at the exhaust port. Okay. What percentage of available energy is typically converted to mechanical work? How efficient are our engines, roughly? 30%? Yeah, 40% is optimistic. Some of the newest car engines are hitting 40%, but yeah, they're not really that efficient. This is one advantage batteries have, is they're more like 90% efficient, but gasoline has got lots and lots of energy in it, and we only use a little bit of it. What happens to the rest of it? Exhaust. Ooh, not quite. Talking about cooling systems. It turns into what? What form of energy? Heat. Thank you. It gets turned into heat. And then we're trying to get rid of that heat. The exhaust is quite hot, so a lot of it is lost in the hot exhaust. And then, or hot cylinders or whatever. It's all turns into heat. Okay, what happens inside the cylinder if temperatures get too high? We just talked about this. I drew some nice pictures. What problem do we get? Effects of behavior, yeah. Impairs lubrication. Causes detonation was actually what I was looking for. And that's sort of like step one you've got there. How do fins help cool the cylinders? What do they increase? Surface area, thank you. If you've got small area of fins that are cracked, damaged, missing, what's our concern then? Is it heat transfer via radiation? Well, it's conducted to the moving air. So radiation would be turning into electromagnetic energy. It's simple conduction to cold air. Hot spots. Thank you. That's what we're concerned about, is a hot spot. The whole cylinder doesn't get hot. One particular spot gets really hot. How does enclosing an air-cooled engine actually improve cooling? Right, we're able to control the airflow. Yeah, we can force the air to flow where we want it to go. So counterintuitively, enclosing the engine actually improves our cooling. It makes it more even. You know, like we might end up with better cooling on one cylinder if we didn't enclose it, but we wouldn't end up with good cooling on the other cylinders. So where would you find a blast tube? In the baffles, yeah. And what are they going to cool? Name a couple of items that might get cooled by a blast tube. Ignition leads, sure. What about some others, folks? Sort of related to the blast tube, a lot of you inspected the shrouds on what part and found them to be bent.
Tim sleeping so soundly.
Lots of folks wrote snags for out of round or bent shrouds over what part on your engine? Fuel system, right, the fuel pump. The fuel pump would get a blast tube to keep it cool. Magnetos will get blast tubes. Alternators will get blast tubes. Okay, what can happen to an air-cooled engine if power is reduced at high speed and altitude? Shock cooling. Did Mr. Cliff talk about what shock cooling is? Yes, okay. And we know that it's bad. How do cowl flaps control engine temperature? More particularly, do they control the airflow in or out of the engine? Out of the engine, yeah. So if the air can't get out, more air can't get in. It's really weird. We don't bother controlling the indoor. We just control the outdoor. During ground operations, on a cold day, do you close them? Help the engine warm up a little faster? No. They should be open all the time on the ground. And then what position should they be in flight? They're usually mostly closed in flight. Why? To reduce drag. Yeah, they stick out in the airstream and slow you down. So we don't want them sticking out in the airstream. We want to stay streamlined in the air. Okay, exhaust augmenters. How do they aid in engine cooling? They help pull cooling air in. Yeah. Exhaust augmenters, do they help cool the exhaust? Do exhaust augmenters, are they there to cool the exhaust? No. Correct. They are not there to cool the exhaust. They are there to cool the engine primarily on the ground. When we're in the air, we've got plenty of cooling. When we're on the ground and the engine's working hard on a takeoff roll, we want extra cooling over the engine because it's working very, very hard. So primarily they help cool the engine on the ground, and they do that by taking the high-speed exhaust and using it to draw in cooling air, and that cooling air gets pulled over the engine. Okay. If you find cracks in your cooling fins, what can you do? Stop drill them, file them. Yeah, you can remove a section of fin. Yeah, you want to stop that crack from going any farther. What happens if a air seal is torn or missing? Looking at this next question. Replace it. Are you talking about the air seal? Well, you should replace it, but what's my concern if I don't? Yeah, the air will flow, but it won't flow where I wanted it to flow, so my cooling fins won't get cooled. Okay, liquid and air cooling systems. What's the advantage of them, of each of them? Give me some pros and cons. We use a lot of air cooling in aircraft engines, and we use a lot of liquid cooling in car engines. So each must have an advantage. What's the advantage of air cooling system? It's light. They're not free. We got all the baffles and special cowls and all the rest of it. But they're lightweight, they're simple, and they're relatively inexpensive. What's another advantage of something being simple that we care about very much in airplanes? They're reliable, right? They also don't have problems in cold weather, right? The air cooling systems. Okay, yeah, less weight, less complexity, less breakdowns. Okay, so with all of these advantages, I challenge you to find a car anywhere being produced today with a air-cooled system. They're all liquid-cooled. So what are the advantages of liquid cooling? consistent temperature control on the whole engine. That's the best part. They work at idle, they work in traffic, they work at high speed. You get consistent temperature control. The engineers know exactly what temperature the cylinders will be. Much better fuel efficiency, much better fuel emissions or exhaust emissions. Okay. Moving along. And this was a Kahoot question. And now it's on this question sheet here. So this ought to be a hint. If you don't use the oil dilution system the night before, can you use it the following morning? No, it'd be a waste of time. Okay. And a lot of you got that wrong, so I don't know what to say. We'll find out tomorrow. What indication would you get of a leaking oil dilution valve? Oil pressure low. Yeah, especially at idle when you first start the engine. Once, why would you get high oil temperature? I don't understand why you would get high oil temperature if you had fuel mixed in with your oil. That's what the textbook said. Oh, okay. Okay, I don't recall that, but I'd be more looking for the low oil pressure. If you get large fluctuations, especially from 0 to full pressure, what does that usually mean? Very low oil quantity, yes, almost out. When is pre-oiling required? After overhaul or long-term storage, yes. Also a new engine. Why do we do it? If parts are dried out, we don't want to go straight to full work. Okay. Okay. There were like 6 functions of oil in an engine, weren't there? Name them. Yeah, you do this before you start the engine. Name me some functions of oil in an engine. Lubrication, obviously. Yeah. Cooling. Yeah. Sealing. Yes. Cleaning. Corrosion prevention. Hydraulic. And cushioning. Nice. All right. Make sure you know those. What type of lubrication do the piston rings typically use? Of those 3 choices. Hydrodynamic, right? It's like water skiing. And I already asked you why they wear more at top dead center than the bottom, because combustion's up there. What type of lubrication do the main bearings use? Pressure, spray, or splash? Pressure, thank you. How is oil delivered to the cylinder walls? Splash or spray? Yes. Next question we've already basically answered. When do you use a non-ashless dispersant oil? When do we use cheap oil? A non-AD oil. When do we use that? Break-in, right. Breaking in, so what's that going to be? A new engine? A overhauled engine? Or what other time? Well, new or overhauled, yeah. Both times, yeah. Or what other time? There's a third. No, not after long-term storage. We would not want to use that for long-term storage. We use a special preservative oil for long-term storage. We change our oil every 50 hours. But there's going to be a time There's 3 times in the engine's life, or 3 situations that we want to use a non-detergent, no scuffing additives, no anti-scuff additives oil. I know I covered it. Wintertime, no. What do we use in wintertime? What do we change in the wintertime? Preheat, yeah. But what do we change about our oil for winter? We're going to use a different oil in the summer and the winter. What do we change? Multigrade or simply a lighter weight oil, or a lower viscosity oil. Right. But we're going to use this oil. Most of the time we want the anti-scuff additives in our oil. There's 3 times when we don't want anti-scuff additives. One is a new engine, so we can break it in. One is an overhauled engine, so we can break in the overhauled engine. There's a third one, specific to our aircraft engines. No, not post-storage. Why would I want to use low-quality oil after I've stored the engine? I'm just going to start flying it again. I'm going to put in my best quality oil and go flying again. This one's come up twice, and I don't know where that came from. I certainly didn't teach it. So prior to storage, we put in a storage additive. And when we come out of storage, we start the engine, warm it up, flush out all that storage oil, and put in a regular high-quality oil. But there is one time that I'm going to, no, why I would use the best oil on long trips. Come on, folks. I taught this yesterday. What can we change on these engines? What can we replace on these engines? Individually. Cylinders. Thank you. What if I put a new cylinder on my engine? Is it broken in? No. So I need to break it in with the same break-in oil that I would break in the whole engine with. So if I replace a cylinder or two, I effectively have done a partial overhaul. And so I need to break in those cylinders. And it's not going to be good for the other cylinders, but that's the way it goes. All right. Okay. So when is non-ashless dispersant oil used? After overhaul, when you have a new engine, or when you change a cylinder, where you do it for about 20 hours or so to break in that cylinder. How do you tell the difference if you've got an AD or a non-AD oil, typically? What code tells me? The W in front. Thank you. How are the 2 rating systems different between SAE? Correct. Sean, correct. Yeah, roughly doubles it. Okay, so what's the advantage of mineral oil? Yeah, in SAE, the W means winter. We use a lot of mineral oil in our aircraft reciprocating engines, even though they're $60,000 engines, and we'd want to give them the very best in the world. And then we use this relatively cheap mineral oil all the time. Why? Because it's cheap? I just said it's a $60,000 engine, and we've got pilots that are happy to spend top dollar, and we still give them mineral oil. Holds particles well, correct? And what does Synthetic oil, not play well with. Lead, correct. Synthetic oil does not work well with lead. And we've got a lot of lead in our gasoline. So in our cars, we can use synthetic oil because we don't have leaded gas anymore. But in our airplanes, we have to use mineral oil because we've got lead in the gas still. In fact, there are some new engines. The Rotax engine will run on leaded or unleaded fuel. And if you run it on leaded gas, you need to change the oil every 25 hours. And if you run it on unleaded, you're allowed to move it to 50 or 100 hours. So that answers the next question, because we've got leaded gas and we've got air-cooled engines. All right, what's the advantage of a multi-viscosity versus a monograde? Correct. So in general, we like a high viscosity index. That means that the viscosity doesn't change much. How do we measure viscosity? I think I had this in here. Functions. Here we go. It's just coming up there. Okay, so why are straight weight engines sometimes recommended in engines that are used infrequently? Because then the oil will stick to the cylinder walls. Yes. Okay, it's 11. I like going through this, but I also want to make sure we teach plank. So I think maybe I'm going to pause on this. No one has like proactively asked me questions about this. So I'm going to stop on this and I'm going to teach you plank for a little bit because that's got to get covered. Where's my plank notes? I'm just looking at the time. Practical projects. 5222. Okay, let's switch here because I'm just looking at the clock and I want to give myself an hour to teach plank. We might not get through all of this because there's a ways to go. Okay, on to plank. All right, I'm going to teach something different for a bit. What time did we get back? 10:32. We're good. We're good. All right, plank. Get your pens and papers out. I'm going to teach you something that is actually kind of useless, but it's in the program. I was pushing to get rid of it, and then one of our instructors talked about the value that he saw in this way of plank is not on the test, no. But plank is due. Let's take a look at your here we go. Plank is due Tuesday. No, hang on. This is the wrong one. That's July and August. P3 engine calculations. Are going to be due tomorrow. So you need to work on those. You've started some of it, but you haven't learned plank, right? You guys all found the P3? Yeah. Okay. And you've been able to do some of the questions, right? But you have not. Were you able to do the plank? You just looked it over. All right. Okay, because I'm getting a whole lot of dead silence when I ask questions here. And I need to go through plank at least quickly to get that covered. I'm happy to spend time on the review, but I kind of feel like I'm not giving feedback to you folks so much as just giving you the answers. And I would prefer if it works the other way around, where you give me your answer, and if you get it wrong, I will explain that. So you had a eureka with it? All right, I'm going to run through Planck fairly quickly then. Sounds like most of you just sort of tackled it. All right, so what is this? PLANK. This is a way of understanding power in an engine. P, pressure. This is measured in PSI, right? We're going to give you an IMEP. This is the average pressure on the stroke length. L is the length, G, T, and this one deserves a great big fat star, because how is that measurement given? And here it's in feet, but how do we always give you the length of the stroke? In inches. How do you convert from inches to feet? So that's inches divided by 12. So you need to make sure you do that. I will get routinely answers that are out by a factor of 12. And that's why. A. This is the area of the piston head. How do we get that? I r squared. When I give you the bore, that equals the diameter. So r equals 1/2 of the diameter. So if my bore equals 6 inches, my diameter equals 3 inches, and the area equals pi times 3 squared equals roughly 27. You folks with me for the area? So what do you get if you multiply area in square inches times pounds per square inch? What do we get? Square inches cross out and we get pounds. So these two work together to give me a force. This one is a distance. What do I get if I multiply force times distance? Work. So this is a way of describing how much work we get on each stroke, each power stroke of the piston. I get a pressure in an area, so it gives me a force, and a distance in feet, that gives me work when I multiply the two together. N, this is the RPM. I have to divide it by 2, because only every second stroke is a power stroke, right? One stroke is an off stroke. So if I've got an RPM of 2,000, I'm getting 1,000 power strokes per minute. And then K, for whatever reason, is Canumber. Okay, so I take all of this. This is the number of cylinders. All right, so I've got the Canumber of cylinders. I take all this and I divide it by 33,000. Why divide by 33,000? Because there's 33,000 foot-pounds of work per minute equals horsepower. So common mistakes. People forget this one here. The length has got to be divided by 12. Another common mistake. They forget the RPM's got to be divided by 2. Sometimes they mess up the fact that the bore is twice the diameter. So radius is half the diameter. It's fairly complicated math. It's a way of understanding what goes on inside of the engine. The reason it was actually Mr. Patterson that convinced me to keep this. He says, which of these things can you change in an operating engine? Can we change the pressure in the cylinder? Can we change how much pressure is developed in the cylinder? Yes. How? Move the throttle plate farther open. Oh no, we can't change that doesn't change the pressure in the cylinder. The PSI is 200 PSI or 250 PSI or whatever. And we can change that. Okay. Can we change the length of the stroke in our engine easily when it's operating? No. Can we change the area of the piston head? No. Can we change the RPM? Yeah, quite easily. And what about the number of pistons? No. Okay, so what he really liked about this is how it showed that we could change the power output of our engine by playing with those two variables, the RPM and that pressure, which is basically our torque. Where's my plank teaching stuff? I thought I had that handy, and I don't know where I set it. I had some sample questions. Sorry, hold the store just a little bit here. Let's take 5 minutes while I dig up the piece of paper that I thought I had out and handy for myself. And you can take a look at this and try and get your brain around it, and we'll be back at 11:10. How's that? Because I thought I had my paper handy, and I'm digging for it, and I can't find it. All right, found what I was looking for. So let's try one or two here, and then I will post this up for everybody to play with, so you can have some samples to work with. Okay, so coming here, let's hit an IMEP. P equals 144 psi. So this is the average pressure when we go from the top of the stroke to the bottom of the stroke. It's fictitious, right? Because at the top of the stroke, it will obviously be much higher than 144. At the bottom of the stroke, it'll be significantly lower. Halfway down the stroke, we're going to, or 2/3 of the way down the stroke, we're going to open the exhaust valve and not even use it, but it's a useful comparison tool. Okay, we've got a 4-inch stroke, a 5-inch bore. It's turning at 2,000 RPM. It is 6 cylinders, and I even go so far as to say it's got a clearance volume equals 11.2 cubic inches. There's a lot we can work out on this. Okay, so what is the horsepower? What is the displacement? What is the compression ratio? Horsepower, displacement, and compression ratio. See if you can figure those three out. 171 horsepower. Right. That was fast. Had you already done this? Have I given you this question before? Or is Mr. Cliff, was it on a sign somewhere? Or did you figure it out that fast? Is that on P3? Oh, good. All right. What's the displacement? You understood it quite well? Okay. There's always somebody who doesn't understand this. I'm going to work through one. I'm not going to spend a ton of time with it. If you're stuck, we can reach out and try and figure this stuff out together. All right, so P is 144. L is times 4/12 times A. So to get A, we need to do 2.5 squared times pi equals what? What is that? 2.5? 2.5 times 2.5 times 3.14 equals 19.63 times n, that's 2,000 divided by 2 equals 1,000 times k is the number, that's 6, all divided by 33,000. And that will give you 171 horsepower. All right, anybody want some help with that? Or does this all make sense? You're confused. Okay. P-L-A-N-K. P, here's my pressure. Let's go with some colors here. There's my pressure there. There's my pressure there. You see that, Aiden? Have I got you? Okay. L, the length of stroke. Pressure is IMEP, yes. The length of stroke. Now here, I gave it in inches, but don't forget that L has to be in feet. So that's where I did 4/12. I got you there. Okay. A, did you follow my area calculations? Oops. Pi r squared. This is pi r squared. That's the area of a circle. Okay. N makes sense, right? 2,000 RPM becomes 1,000 power strokes per minute. And then K. Okay, so Aiden, and then we divide the whole thing by 33,000 to get 171. So which part still is confusing? Yes, because what this gives us, let's skip forward a page. Let's just go here. Oops. I started with P, L, A, N, K. What are my units? P, S, I, right? Pounds per square inch. L is in feet, right? A is in square inches. N is just a number and K is just a number. Pardon me, N is revolutions per minute, or this is number of times per minute, RPM. So my square inches cross out, right? Because I had area in square inches and pressure is in pounds. This should be make this in pounds. LBS, this is LBS, pounds. So what I'm left with is pound feet per minute. This is all going to turn into how many pound feet per minute. Now, 1 horsepower equals 33,000 pound feet per minute. That's the definition of a horsepower, is 33,000 pound feet per minute. So when we divide by 33,000, we get horsepower. All right? Seems like I've got you with me now. Okay, so that would get all of that covered. The cubic inches. Let's do that real quick. So my cubic inches, going back a couple of slides here. Let's erase all of this stuff. Come on, go away, go away, go away. Erase all of this. Now to get my cubic inches. Now we don't need to worry about this silliness of converting in and out of feet. We can simply go with a 5-inch bore. So the area equals, if I've got a cone, remember, why mix inches and feet? The reason is horsepower is 33,000 pound feet of work. And so to get horsepower, I either need to use 33,000. You could instead of using 33,000, you could not do that. Instead of dividing by 33,000, you could divide by whatever 33,000 times 12 is. Does that make sense? Like we're dealing with foot-pounds of work per minute. So I need to convert my inches to feet for that Planck formula. Have I got you with me or not? I'm not sure that I do. 33,000 foot-pounds of work. But the stroke, remember, was given in inches. So my piston, why do we convert the stroke and not the bore? Okay, because that 33,000 is in foot-pounds, but the bore, we're trying to get rid of this PS. I've got pounds per square inch is my pressure, right? And my area is in, if I leave my area in square inches, these two will cross out. Does that make sense? PSI times area PSI times area in square inches, the square inches will cross out and I'll be left with pounds, which is what I wanted for my formula. Good questions. All right, so to calculate displacement, I've got a 5-inch bore, which means I've got a 2.5-inch radius. So I need to do pi times 2.5 squared, and that came out to that 27.69, I think it was, square inches. And I multiply that by the length of my stroke, which is 4 inches, times 4 equals whatever that is, 2.5. Let's do the math. 2.5 times 2.5 times 3.14. Pardon me, this was 19.625. Oops. 19.625 or 6. You got 634. You've used a better version. Times 4 equals 78.5 cubic inches times 6, because this is this, so that's the area, that's the stroke, and then this is the number of cylinders, and that will equal times 6, 471. All right, have I got everybody with me for the displacement? All right, anybody need some extra on displacement, or are we good? All right. Yes, always, the displacement we're asking for will always be engine displacement. Yeah. All right, get rid of all this stuff. Now, we've got 471, we've agreed, is my, I need a wider eraser on my pen here. Okay, so 471 is my swept volume. What's my clearance volume? 11.2, right? But that's going to be for one cylinder. So I need to either divide this by 6 or multiply this by 6. Because you can't do the clearance volume for one cylinder and the swept volume for the whole. So let's divide my 471 by 6. And I get 78.5 plus 11.2 will give me my total volume. So plus 11 equals 89.7. Yeah. And it is then 11.2 over, pardon me, wrong way around, 89.7 over 11.2 equals 8:1 compression ratio. Okay, so what I'm going to do, for those of you who are not quite with me, I am going to, after class is over, put this document that I made with a bunch of sample questions and the answers. I'll put that up on the D2L, and you can work your way through them and check your own math. And if you're stuck, you can reach out to me and I'll help you figure out where you're going wrong. That sound like a reasonable way to do this? Okay. I'm assuming most of you would like to, if I went back to this will not be on the test, but it is part of that P3 practical. This doesn't seem like the fair kind of math. Yeah, we're going to work back on the review sheet. Okay, but I want people giving me answers. I'm not just giving you the answers. So, cooling and lubrication. Because the idea of this is not that I give you all the answers. The idea is that you work your way through them and you tell me the answers. So if people don't give me the answers, their answers, in reasonable speed, I'm going to just cut things off. Like if nobody's actually done this, I'm not doing it for you. Okay. We've covered all of this. All right, metal sludge inside of a filter. What do we do? If folks have done this, you should have answers in front of you and ready to type out. And if nobody's done it, that is normal, right? Okay, why do we need to do oil filter inspections even if we've got a soap program? Right, to look for large debris that the soap program can't pick up. Okay, what types of problems is the soap analysis good at detecting? Slow wear events, exactly. Microscopic is what it can detect. All right, functions of oil and engine, we've done that like 3 times. What is viscosity? Resistance to flow, exactly. How is viscosity typically affected by temperature? Temp up? Yes, exactly. Okay, how does this fancy Seybold universal viscosimeter work? Oil in a tube brought to temperature, 60 cc, and we use a timer. Thank you. Perfect. What is the difference in the W? I think we know that one. It means winter for SAE and what you call it? Ashless detergent for aviation. Yep. Does the SAE rating tell you anything other than the viscosity? You know the quality, synthetic? No, you don't get anything other than viscosity. Why do we prefer high viscosity index? Detergent for what? It's like the cleaning ability. So one of the 6 functions or 7 functions, depending on how you count it, of oil is to clean the inside of your engine. So if you added a little bit of soap it would do a better job of cleaning. So they use a special detergent, a special soap into the oil. Does that help you, Mertcan, I hope? Right. And in general, we want a stable viscosity, whatever viscosity we decide the engine is designed for. We want that at all temperatures. Ideally, it would never change. So we use a multi-viscosity oil so that as the oil heats up, it generally, it keeps the same actual thickness. Specific gravity. What is specific gravity? Fluid's density compared to water, actually, but pretty close. Okay. Where is oil stored in an engine with a wet sump system? In the bottom of the engine, in the sump. Which system is simpler, wet sump or dry sump? Wet, yes. If we didn't vent the crankcase, why would it get excessive pressure? Thermal expansion? Ooh, no. I'm talking about the crankcase. What's the biggest source of unwanted pressure in our crankcase? Blow-by. Thank you, blow-by. We've got hundreds of psi, depending on how you count it, of air pressure above the piston, and we've got, relatively close to zero below the piston. Where do you think that air wants to go? It wants to go from above past the piston rings into the crankcase. And if we don't let it out, the crankcase will eventually inflate. So we have to vent the crankcase. Why do the main bearings of an engine always get pressure lubrication? Nobody put an answer for this? Well, splash lubrication can. They're down in it's right above the sump. They are the hardest working bearings in the engine. Tremendous loads. What kind of force do you suppose we've got? Let's go back to that plank. What was the square inches of our piston? Roughly 27? Sound about right? And what was the pressure? 200 psi? That's the average psi. So at the top, it's got to be at least 400. Fair? What's 400 psi times 27 square inches? Somebody pull out their calculator. What's 400 psi times 27 square inches? This is the kind of pressure we're going to get at top dead center. And in fact, it'll even be higher than that. 11,000 pounds pushing on our piston. So can you see that we need a very robust bearing to handle 11,000 pounds suddenly hitting it? Okay. Dry sump engines. Why do we always put the oil tank high? Gravity feed to the oil pump. What do we do to allow for oil expansion and foam when the engine's running? Because you got this scavenge pump slurping and sucking, and it's going to gulp air. It's supposed to. It's going to foam up our oil. Extra space, and the tank filler neck is just put below the top, so you can't actually fill it full. Okay, so why do we vent the dry sump engines? Why do we vent the tank into the crankcase and then from the crankcase overboard, rather than just venting the oil tank straight overboard, which would be simpler and easier to do? To prevent the loss of oil. Thank you, Raiden. What do we put into large radial engines to speed the oil warm up? A hopper. Correct. Why do some, in fact, most oil pumps, if it's a dry sump, draw the oil through a standpipe? We're trying to leave some oil behind when we use that standpipe. What are we leaving the oil for? Propeller feathering. Thank you. Emergency operation of the propeller feathering pump. Most engines, how do we check the oil? Dipstick. Yes, really simple. Super simple. What type of pump do we use to pressurize the oil? A gear pump. Positive displacement. Thank you. What turns this pump? Pilot? Is that pedals in the cockpit? The crankshaft. The engine itself. Spline drive shaft from the crankshaft, sometimes from the camshaft. Why does the oil filter have a bypass valve? We talked about this yesterday. There's 3 different valves. There's the oil filter bypass, there's the oil cooler bypass, and there is the pressure relief valve. Why does the oil filter have a bypass valve? Clogged filter, right. We want to make sure that our engine gets oil no matter what. It won't be filtered, it won't be clean, but it's better than nothing. Okay, what is the most common type of filter in use today? Oil filter. Full flow, disposable, spin-on. Yes. How do we regulate the oil pressure on our engines? Regulating valve. Pressure relief valve. Thank you. That pressure relief valve that you assembled. Remember, it's got that 13/16 stud that's supposed to stick out, and that puts pressure on a little spring to hold the valve closed. Okay, where is oil pressure usually measured? At the outlet to the pump. At the outlet of the pump, yes. How do multi-engine aircraft often display the oil pressure? On one dial. Yeah, combination gauges. And do you put oil and temperature on one gauge, or do you put both oil pressures on one gauge, oil temperatures on another gauge? How do we group this stuff? Both pressures on one gauge, both temperatures on another gauge. Yeah, it's much easier for the pilots to read and see problems developing. Okay, what gauges do we usually give the pilots? Oil temperature and what other thing do we tell them? Oil temperature, oil pressure. Thank you. How is the oil temperature regulated? We don't want our oil too hot. We don't want it too cold. Oil cooler, right. That cools it, but how do we prevent it from cooling it too much? Thank you, Braden. Oil cooler bypass is open when it's cold, right? Because the oil would rather not go through the cooler. So this will be a thermostat. Changes its shape based on temperature. Okay, so when is it farthest open? Oh, and there's 2 methods to regulate it. One was to allow the oil to go through. What was the other? One is control the oil flow through the oil cooler. What's the other method of regulating oil temperature? Airflow. Thank you. we can control more or less cooling air over the cooler. Sankook, the bypass is sort of the first method, that bypass valve for oil going through or around. Okay, so when is the bypass valve farthest open? When the oil is cold, right. Bypass the cooler. We don't want it to go through the cooler. It's already cold. How does oil get to the bearings on the connecting rods? The big end bearings. Right. Thank you, Braden. What about the small end of the connecting rod? Splash or spray. That's a hard-working bearing, and they don't last as long. Okay, why does the scavenge pump have greater capacity than the pressure pump? To keep the sump dry, right. All right, and asking this one again, figure 617, the air intake tubes go through the oil pan. What are we trying to do here? Cool the oil? Absolutely not. We are not trying to cool the oil. We have an oil cooler for that. Braden's got it. We are preheating the fuel air mixture. We are preheating. The reason for this is not to cool the oil. We use our oil cooler for that because we can regulate it. Yeah, well, whatever. You got it right. So that'll help him tomorrow. Okay. Or maybe he just read it, because they tell you that if you read the words. So all of these questions, don't just guess, read the words. Okay, why do airplanes need to use a dry sump oil system? Well, a wet sump won't work very well upside down. Another question here. How does the oil pickup work if you've got a dry sump system and you fly upside down? How do we still manage to pick up oil? Anybody know that? Standpipe, well, that won't work. They use what's called a clunk, technical name. They put a rubber hose section in the oil tank with a heavy bit at the bottom, and it goes clunk when you flip the tank upside down, and it clunks to what was the top of the tank, where the oil all is now. When you fly right side up, it clunks to the bottom of the tank. They just took a hose with a weighted fitting at the end of it, and it just clunks around and follows the oil. All right, how are we doing, folks? We're on page 7. I think we're going to push through here, aren't we? And okay. Why must engines be preserved if they're not going to be run for an extended period of time? What are we trying to prevent? Corrosion. Thank you. How long and how often does Lycoming want their engines run? At least once every, fill in the blank here, folks, 30 days. How long? 1 hour. Can this be done on the ground? No. Why shouldn't we rotate the crankshaft of a stored engine? Preserve the preservative, yes. What steps should be taken to prepare an engine for storage? I gave you 7 steps or 6 steps. List them back to me. Put the blue plugs, yes. That's 1. Intake covers, yes. Put in the reservative oil, then run the engine, yes. Put desiccant in the exhaust ports. Yes. Where else do we want to put engine preservative? Into the cylinders. Yeah. I think we got everything there. Okay. What check should you do every 2 weeks? Desiccant check. Make sure the plugs are still blue and just a general peek around at stuff. Okay, why do we want to rotate the propeller prior to returning the engine to service? What are we checking for? Hydraulic lock. Thank you. Okay, any special tools required to lap a valve? Lapping tool. Well, the valve itself is the lapping tool. We put lapping compound on the valve, pull it in position, and just turn it by hand. So there is no special tool for lapping the valves. We use it's called valve grinding compound. I have it in my toolbox. I've never lapped a valve. I use it on my screwdriver tips. Okay, what is the simple check that the FAA recommends for checking for the valve seating when the cylinder is off the engine? Glow plugs? Huh? So if you want to make sure that the valves seal, what am I supposed to do with a glow plug, Mertcan? Turn the cylinder upside down, put the valves in place, put some kerosene in. If the kerosene doesn't leak out, then we're good. Okay, what is the most common cause of low compression? Leaking valves, yes. I have seen engines with bad rings and bad cylinders. I have seen many engines with bad valves. I have never seen an engine with bad rings that did not also have bad valves. It's always the valves. Sometimes it's the rings as well, but it's always the valves. I mean, there's no reason that it would have to be that, but it is. It's just what you'll find. Okay, why do we do a compression check immediately after running the engine, as opposed to walking out on our time and dealing with a cold engine that's much, nicer to work on? It's at operating temperature, right? It's the shape that it's going to be. You'll get better numbers if you've got round pistons with lots of lubricant than you will with oval pistons in choked cylinders. You want everything hot and at its proper shape. Okay, so if you get a poor test result, what might you do that's perfectly legal to improve the numbers? Right. You can do that, spray some oil in there. You can also, according to Continental, just go for a flight and try again. All right, why does the piston need to be at top dead center on the compression stroke? Because it's the only place where both valves are closed. Yeah, and if you're not at top dead center, you'll never hold it still, because remember we calculated 11,000 pounds of force? Okay, we'll only have 2,000 pounds because we're going to do 80 psi, but still, I can't hang on to 2,000 pounds. Okay, now here's some stuff, specific things. I'm not sure how much Mr. Cliff talked about it. How do you identify oversized studs? It has markings. Where are the markings? On the end of the stud, absolutely. So you've got loose studs in your engine. In fact, a couple of you did in Mr. Cliff's class, really loose studs. So we go and grab an oversized stud because we don't want to throw out the whole crankcase and the whole engine. We want to grab a slightly bigger stud. How do you know if you grabbed the right one? How do I know I got the Goldilocks? It's not too small, not too big. Anybody read Continental OHM 5-18? Go one size bigger than the one you had. Okay, well, sure. But is that enough? I don't think anybody read this. So I'm not going to give the answer. Okay. Why is it important to use the proper tool when removing a helicoil insert? And by the way, Josh, that's the wrong answer. So it seems like the whole class needs to read Continental OHM 518 before their test to answer those three questions. Wasn't very straightforward. Well, no one has any answer for me. So how are oversized all three questions on 518? How do you know if a stud's been installed far enough? Okay, so we've got that one. Okay. All right, well, it does seem like a couple of you read it, and you know how they're identified. The way you know if you got the right oversized is by how much torque it takes to install it. If you got the right sized, the correct oversized, it will take a certain amount of torque to twist it in the hole. If it is too tight, then you've got too big of too thick, too big a round of an oversized stud. If it's still too loose, you need to go one bigger. If you get to the maximum oversized and it's still too loose, then you're looking at a new crankcase. Does that make sense? Okay. You'll know you got the right one when the torque is correct, and you'll know it's in far enough when the distance is right. Okay. Removing bushings. Okay. If you're trying to replace bushings and you want to put a new bushing in, which part are you going to heat, the bushing or the casting? And then you refrigerate the bushing, slide it in. All right, we've made it through here. Any other questions that you folks didn't quite understand? We covered a lot today. So that plank P3, it sounds like everybody's found it. That's due tomorrow. Sounds like most of you are well on your way. You got my email, you got my phone number. What was the most common cause of low compression? Bad valves. How cowl flaps operate? Sure. Let's get slideshow. Uh-oh. This isn't good. Monitor. Hang on, it's in here. Escape. Slideshow. Here, I'll just go down here. Let's just make this one big. This will work. Okay, here's cowl flaps. So, airplane is flying forward. This area here makes a low pressure zone, and high pressure ram air hits here, and this is a bad drawing. these should be blue and these should be red, right? The arrows on top are cool air getting rammed in, hits the back wall here. And in fact, when we go to this pressure cooling system, that's what this is called, pressure cooling, the rear cylinder often gets better cooling than the front cylinder because the air impacts and doesn't go down till here. But the upshot is we get pretty good control of our airflow. And when we're in flight, we've got lots of air going down here. In fact, we've got more cooling than we need. So we close the cowl flap here. And here's a picture of a cowl flap. So you can see when we're on the ground and we want more cooling, we open up that exit wider and generate more low pressure here and more cooling air. When we get up into flight and we've got lots of cooling and we want to streamline, the pilot will move this up, close this door a little bit, and get less cooling and better streamlining. That help, Braden? Correct. It allows more air to escape. And this is called pressure cooling, and it depends a lot on differential pressure. And especially in flight, we make a low pressure zone right here. And on the ground, we don't get much of a low pressure zone, so we need to do everything we can to get better cooling. All right, I think just about ready to take attendance and call this one a wrap. Okay, let's go. Evan, Sukran, Sean, Rudy, Travis, Aiden, Christian, JP, Eli, Mark, Josh, Ronan, pardon me, Harbir, Andy, Isaac, and where's Isaac? There we go, and Yin. Okay, and Satnam. Okay, is that everybody from 378? Somebody said I was missing them yesterday. I think I got everybody here.